Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about graphs. A graph, G, is a collection of vertices and edges. Consists of a set V of vertices and a set E of edges. So you have a bunch of vertices, but you may also have edges. Here, we assume that the vertices set is not empty. It's not the empty set. There has to be something in there. We also assume each edge is connected to one or more vertices. So we're not going to have edges out here not connected to vertices. It has to be connected to some kind of vertex. It could have only one vertex that it's connected to. It could loop around back onto itself. So those are the possible edges that we can allow, but not something that's disconnected from vertices. Each end of an edge must be connected to at least one vertex. A graph is called infinite if the number of vertices or edges is infinite. Otherwise, it is called finite. Now, in this course, we're only going to deal with finite graphs. So it's possible to have an infinite number of vertices going off forever and edges etc. But we're only going to look at the case where this actually comes to a definite end someplace. By the way, computer networks form graphs. You could have a whole bunch of different servers or computers all connected perhaps by multiple different ways. Forming a graph. By the way, an edge with both endpoints at the same vertex is called a loop. So here we have a loop right here. However, graphs with loops are sometimes called pseudographs. Pseudo being a prefix that means false. So sometimes we look at strict graphs with no loops. If it has a loop, it's called a pseudograph. A directed graph or digraph is a graph, but each edge is directed. So let's suppose we have a directed graph, something like this. We have to put a direction on each of these. We might have directions both ways, but we don't have to. And here is a directed graph. Of course, with the loop, it might be a pseudo digraph. So we might go for strict graphs that don't have these directed loops. A simple graph, digraph, is a digraph, so a directed graph having no loops. Okay, that's one feature, but also no pair of edges is connected by more than one edge. So if I have something like this where, let me reverse that arrow there. This would not be simple because you have two edges connected to the same vertices. We can have something like this. And this would be a simple digraph. If two vertices have more than one edge, the digraph is called a directed multigraph. So this would be a directed multigraph, where this is just a directed digraph. In a directed multigraph, if vertices u and v are connected by m edges, we say that vertices u and v have multiplicity m. So the multiplicity of a pair of vertices is the number of edges that connect them. So you can have vertices u and v connected by 3 edges, so this would have multiplicity 3. A graph having both directed and undirected edges is called a mixed graph. There are a number of interesting examples of the use of graphs in your text, and so I suggest that you go read those examples out of your text. But now some more terminology. Two vertices of an undirected graph are called adjacent if they are connected by an edge. So I guess you can see here that if this is U and this is V, then these are not adjacent. But if this is U and W, they are adjacent. If we call this one Z, over here, U and Z are adjacent, Z and W are adjacent, Z and V are adjacent, but U and V are not adjacent. We also call adjacent vertices neighbors. So these are not adjacent, they're not neighbors, but U and W are neighbors, etc. Such an edge connecting to adjacent vertices we'll call the edge E, connecting vertices U and V is said to be incident with U and V. And E, the edge, is said to connect U and V, as we've just indicated. The neighborhood of a vertex V, it's denoted by in a V and consists of the set of all neighbors of V. What is more, if we have some set that's a subset of the set of all vertices, so we have some subset of that, then the neighborhood of that subset is the set of all neighbors of the elements of A. So if we have U, V, let's say W over here, and we'll put Z over here, what is the neighborhood of the set that contains, let's say, U and V? The set of all neighbors. Well, Z is a neighbor of U, and W is a neighbor of V, so this will be everything. On the other hand, if we have a graph like this, U, V, W, Z, and we'll call this one Y, then the neighborhood of U and V will have Z and W included, but not Y. Concerning neighbors, let's suppose we have the following graph, A, B, C, D. What's the neighborhood of A? Well, everything that it's connected to is connected to B, C, and D. What's the neighborhood of B? Well, that would be A and C. Those are the only things that connect to B, and so on. So note, the neighborhood of some set A is the union for all vertices in A of the neighborhood of that vertex. The degree of a vertex in an undirected graph is the number of edges connected to it, except loops count twice. So let's suppose I have some undirected graph like this. This vertex has 1, 2, 3, 4, so its degree is 4. This one has a degree of 2, and same thing over here. The notation is the degree of your vertex. A vertex of degree 0 is called isolated. Another definition, a vertex of degree 1 is called a pendant, because it is out there by itself, connected to perhaps a whole tree of different possible things up here, but it's hanging down like a pendant on a necklace. We have something called the Handshake Theorem that says if G, with vertices and edges, is an undirected graph of M edges, if you add for all vertices in the set of vertices the degree of each vertex, you end up with twice the number of edges. To see this, let's suppose that we have a graph like this. We have U, V, and W. Here, the degree is 3, degree is 3, degree is 2. So if you add up the degrees for all of these vertices, you'll get 3 plus 3 plus 2, which is 8. That's supposed to be twice the number of edges, 1, 2, 3, 4, which you can see. That has to be the case because each edge gets counted twice. This edge and this edge get also counted when we're considering this vertex, this edge and this edge. This particular edge gets counted both when we're looking at U and also when we're looking at W. It's connected to both U and W, so it gets counted twice. And that's true for all of the edges. They all get counted twice. Even if it's a loop, even if we have degree 5 here, that would give us 10, which would be 2 times 5. 1, 2, 3, 4, 5, just as we said. As a simple application, let's ask the question, how many edges are in a graph of 10 vertices if each vertex is of degree, let's say 5. Well, each of these 10 vertices has a degree of 5, so if you add up the degrees, you're going to have 10 times. Of these 5s, that's going to be 50, which is supposed to be twice the number of edges. So m would have to be 25. As an immediate corollary, the number of odd degree in an undirected graph must be even. You have to have an even number of odd vertices. So let's give an example here. This has degree 3, this has degree 3, this has degree 2. And so you can see 3 plus 3 plus 2 has to be an even number, because if you add up all the degrees, it has to be twice the number of edges. 1, 2, 3, 4. 2 times 4 is 8. You can see that if you only had an odd number of odd degree vertices, you couldn't get an even number as the sum of the degrees. Even number plus even number will be even. If you add one odd number to an even number, you will get an odd number. You have to have an even number of odds added together, because if you add an odd number to an odd number, that will give you an even number. So the number of odd degree vertices has to be even, because of the even number, total number of edges. Suppose we let u and v be vertices in a directed graph, a digraph. And suppose u and v are connected by an edge going from u to v. We denote the edge by the ordered pair uv going from u to v, and say that u, vertex u, is adjacent to v, and v is adjacent from u. So to v is going from u to v. And if it's v first, you just say v is adjacent from u. Here we're saying that u is the initial vertex, v is the terminal or end vertex. For a loop, initial and terminal vertices are the same. In a digraph, the out degree of a vertex u is degree with a superscript of plus, and is the number of edges connected to u with u as initial vertex. And of course the in degree, you can think of this as like a little crosshairs going out. You're aiming something out from you. The in degree has a minus on it, It's the number of vertices, number of edges connected to V with terminal vertex. The number of edges. Loops contribute one to each. The out degree and the in degree. Suppose we have A, B, and C. And here's a directed graph. Suppose that this goes here and this goes here, but we have a loop going around like this. So let's think about the out degree of A. This number of going out, that's going to be 1, but the in degree of A, how many coming in? Well, we have 2 of them coming in. On B, the out degree of B is 1, and the in degree of B is 2. Now how about C? The out degree of C, well, has 1, 2, and 3, but the in degree of C, well, has 1 coming back. There's a theorem about this. If you add up all of the out degrees, you'll get the same thing if you add up all of the in degrees, and that'll be equal to the number of edges, which we'll denote by bars around the set E, the order of the set E, the number of the set containing the edges. So let's see if that's true here. Let's add up the out degrees. 1 plus 1 plus 3 is 5. Now let's add up the in degrees. That's 2 plus 2 plus 1, which is 5. And so we can see this here, and this has to be the case because each edge is connected to 2 vertices. It has 1 in vertex and 1 out vertex for each edge. Each directed graph has an underlying undirected graph obtained by ignoring the directions of the edges. The graph is called complete if it has an edge between each pair of vertices in the graph. So if you have only one vertex, that's complete. If you have 2 vertices, they have to be connected. If you have 3 vertices, each pair of vertices must be connected. If you have 4 vertices, you have to have all of these edges, because between every 2 vertices you have to have an edge. And so you can see this gets more and more complicated as the number of vertices increases. The notation will be Kn is the complete graph having n vertices. So this will be K1, K2, K3, K4, and we can keep going. A cycle, denoted by Cn, n bigger than or equal to 3, is a graph having edges v1 to v2, an edge between v1 and v2, v2 and v3, and we keep going vn minus 1 vn. And we could go from vn back to v1. So here we have an edge between each of these. If we have 4 vertices, here you have the cycle goes from v1 to v2, v2 to v3, v3 to v4, and v4 to v1 again. So it has to end where it began. If you have 5, it'll be like this. So a cycle just has the vertices lined up and then connected by edges one after the other, with no other edges included. A wheel, Wn, is obtained from a cycle, Cn, by adding a vertex and connecting it to each vertex in Cn. So here I have my cycle C3, but if I add one vertex and connect that to each of the others, then I get W3. Here I have C4. If I add one vertex and connect that to each of the others, I get the wheel with 4. It actually has 5 vertices. This actually has 4 vertices for the wheel. An n-dimensional hypercube. That's a mouthful. So sometimes we abbreviate this as an n-cube, is a graph having 2 to the power of n vertices represented by bit strings. Before I get too far into this definition, maybe I should draw something. The bit string here will be 0, 0, and then we'll have 1, 0. This will be 0, 1, and this will be 1, 1. So you can see we can represent these vertices in this way. So this would be a 2 cube. I know it's a square, but it's a 2-dimensional version of a cube. In 3 dimensions, a cube might have vertices like this. And here we would have 0, 0, 0. This would be 1, 0, 0. This will be 1, 1, 0. This will be 1, 1, 1. Back here it'll be 0, 1, 0. And now up top, 0, 1, 1, 0, 0, 1, and 1, 0, 1 right here. One thing to note about the bit strings representing the vertices on an n-cube is that we're going to say that 2 vertices are adjacent if and only if their bit strings differ in at most one, in exactly one place. So these are differing, the 0, 0, 0 differs from 0, 0, 1 in only one place. So these vertices are adjacent. Same thing over here. 1, 0, 0 and 1, 0, 1 only differ in one place, so they are adjacent. They're connected by an edge. 1, 1, 1, 0 and 1, 0, 0 obviously differ by 1. 1, 1, 1, 1, 1, 0 differ by 1, so they're connected. However, if they differ by 2 or more, they're not going to be adjacent, so 0, 0, 0 and 1, 1, 0 are not adjacent. They will not be connected by an edge. And so this will give us the n-dimensional hypercube, otherwise known as an n-cube. You can see this is the 3 cube, the 2 cube, a 1 cube just has 0 and 1. So a 4 cube would have to be drawn in 4 dimensions, which is kind of hard to do here, so I'm not going to do it. But there's higher dimensional cubes even still, 5 cubes, 5-dimensional hypercubes, and so on and so forth. So you can see with dimension 1, you have 2 vertices. With you're in dimension 2, you have 1, 2, 3, 4 vertices. If n is equal to 3, 2 to the 3 is 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices altogether. So 2 to the dimension of the space that you're in gives you the total number of vertices. These n-dimensional hypercubes will denote by Qn. So this would be Q1. Here we have Q2, and this is Q3. A simple graph, so there are no loops, is called bipartite if the set of vertices can be decomposed as, here's your vertices, it's going to be set of vertices 1 union the set of vertices 2, where these are disjoint. There's nothing in common to these two sets, and every edge has one vertex in V1 and the other in V2. So let's see if we can figure out some kind of a bipartite simple graph here. We'll call this A, B, C, and D. Let's suppose we're connected in this way. Then, how can we decompose this set of vertices, A, B, C, and D? Well, let's suppose V1 is A and D, and V2 is B and C. So A is connected to B, and also A is connected to C. D is connected to B, and D is also connected to C. So every edge in this graph can be expressed as starting at some point in V1 and ending at some point in V2, or just connecting points between something in V1 and something in V2. So this is a cycle. This is like C4, and so all cycles with an even number of vertices will be bipartite. Let's look at C3. You have A, B, and C. Every edge has to come from V1 and V2 if this is bipartite. So let's suppose we set V1 equal to, I don't know, A and B, and V2 equal to C. Does every edge have somewhere where you start at A, let's say, and end at C? You start at B and end at C, but we don't have the edge A to B, because you have to start with, say, A and end at B, with the B being in V2. So this is not bipartite. We know that C4 is bipartite. Let's look at K4, the connected graph with 4 vertices. Here would be K4. We'll have A, B, C, and D. Is it possible to put each edge into 2 sets? Let's try A and C here, and V2 as B and D. That wouldn't work because we have an edge that goes from, let's say, A to B. That's fine. But what about A to C? We don't have that. A to C, because we have A here, but we don't have C over here. So that wouldn't work. And so K4 is, it turns out, not to be bipartite. There's an easy test for determining whether or not a graph is bipartite. A graph is bipartite if you can color the vertices so that with 2 colors, color the vertices with 2 colors so that no adjacent vertices have the same color. So let's look at C4. We can go red, blue, red, blue. And then we'll just separate this up into red and blue. If we had K4, we'll have red and then blue, because they're connected by this edge, and each edge has to have one vertex in one set and the other vertex in the other set. This would have to be red then, but then red would connect to red. These would be adjacent vertices in this case. And so you can see it's not possible to color K4, the connected graph K4, with different colors on adjacent vertices. So it is not bipartite. So I'm going to give you an example to try this out. And we're going to have 7 vertices. How are they going to be connected? We'll call this A, B, C, D, E, F, and G. And we're going to have these connected. Let's see. D here is going to be connected over here to F and to G. And then G gets connected to A is connected to F, A is connected to E. Let's see, A is connected to C, and one more, B is connected to F over here. Is this a bipartite graph? Well, let's start labeling the adjacent vertices with 2 different colors. Let's say red and blue. Let's call this one red. It's adjacent to G, which then must be blue. That's adjacent to D, which must be red. Let's see if we can track this over here. If A is adjacent to C, then C must be blue, and blue is connected to red. That's fine. If C is connected to B, this must be red, because that's blue. And so anything connected to B must be, and anything connected to B must be blue. Do we have any contradictions here? Red to blue, red to blue, red to blue, blue to red, red to blue, blue to red. Looks like we have all of the vertices colored. So our V1 will be all the red vertices, A, B, D, and V2 will be all of the blue vertices, C, E, and then F and G. So we have these disjoint sets that comprise all of the vertices when you take the union, and each edge can be represented as a link between a vertex in set V1 to a vertex in set V2. So let's try another one. We'll call them A, B, C, D, E, F. What are all the connections here? All of these around the edges. Yep, A is going to connect to here, we're going to connect to here, and to here, and to here. We'll connect across this way. And let's see, this will have to connect down to here. And I think that's it. Those are all the connections that we're going to have. Let's see if we can color them in such a way, with red and blue, so that no two adjacent vertices have the same color. So we'll have to have red here. If that's red, this will have to be blue. If that's blue, this will have to be red, but then red goes to red, and that's a contradiction. And so this is not bipartite. Complete bipartite graphs which are going to be denoted by KMN, have vertices V1 and V2, where the order of V1 is M, the order of V2 is N. V1 intersect V2 is of course empty, and all vertices are the union, V1 union V2. And what makes it complete? There will be an edge between each point in V1 and each point in V2. Where each point in V1 is connected to a point in V2, of course, by an edge. So an example might be K23. Here we have A, B, C, D, E. Each point in the first set, AB, is connected to each point in the second set. And so those would represent all of the edges in this complete graph K23. Let's look at K33. We'll have A, B, C, D, E, and F. Every element in the first set has to be connected to every element in the other set. This brings up a classic example of marriages on an island. Let's suppose that we have a group of single and heterosexual individuals. So we'll have V1 be the men and V2 be the women. And we would like to make a list of all possible acceptable pairings between the men and the women. We'll say a pair is connected by an edge if they are mutually compatible. A matching is a selection of edges so that each pair ends up married. Which would be a problem if the number of elements in V1 is not equal to the number of elements in V2. So let's suppose we have 2 men and 3 women. We might have this sort of matching that would leave one person left over unmatched. A maximum matching has the largest number of matched pairs. A complete matching is when every member in V1 is connected to a member in V2 and vice versa. You can have a complete matching of V1 where every member in V1 is connected to a member in V2. You can also have a complete matching of V2 where every member in V2 is connected to a member in V1. This would be a complete matching of V1, but not of V2. It's also possible to do this analysis where the acceptability goes only one way, in which case we would have a directed graph or a digraph. It's possible that this goes this way but not the other way. Maybe it goes this way over here. And so we can generalize to these directed graphs. There is something called Hall's marriage theorem. And it goes like this. Let G, with vertices and edges, be a bipartite graph with the bipartition being V1, V2. So the set of vertices will be the disjoint union of V1 and V2. This will have a complete matching from V1 to V2, but not necessarily the other way, if the order of the neighborhood of A is always greater than or equal to the order of A for which sets A? For all A that are contained in V1. So for each of your people over here, or collections of people in V1, the neighbors of that have to be at least as large for each of those. And what is more, the proof goes both ways. So you have a complete matching that implies this inequality for all sets A, but the implication goes the other way. If this is true, then you will have a complete matching. So in the proof, you actually have to prove 2 ways. We'll have to prove complete implies this inequality. Well, that has to be true because if you have a complete matching, then everybody over here in A has to match to someone in V2, and so the neighborhood would have to be at least as large as A. So this is kind of obvious. And so we really only need to prove the other way, that if this inequality holds for all A that are contained in V1, then there will exist a matching. However, the proof uses math induction. For this direction. In particular, it's going to use strong math induction. So let's suppose that the order of V1 is 1. Then 1 is the order of V1. And that has to be less than or equal to the order of the neighborhood of V1 because, so that's the n equals 1 case. for the induction hypothesis, suppose for 0 less than or equal to k less than or equal to some n hat, the order of the neighborhood of A is bigger than or equal to the order of A, where the order of A is k. And whenever this happens, that implies there's a complete matching from A, from V1 into V2. Suppose the order of V1 isn't n hat or something in between, it's n hat plus 1, so it's 1 bigger. So how are we going to construct a complete matching from V1 into V2 in this slightly larger case? Well, just let V be an arbitrary element in V1. Then the order of V, which is 1, is less than or equal to the order of the neighborhood of V. And so that implies we may select W from the neighborhood of V such that V is matched to W. Then consider V1 hat, which is V1 with the set that contains V taken out, V2 hat, which is V2 without W. So by the induction hypothesis, there is a complete matching from V1 hat into V2 hat. To complete the rest of it, all you have to do is add in the other matching, and we're done. Let G, which has vertices and edges, be a graph. A subgraph of G is of the form H, which has W and E and F, such that W is a subset of the set of vertices, and the number of edges in H will be a subset of the number of edges in the original graph. This doesn't preclude the possibility that G and H are the same. So it is a proper subgraph if G isn't the same as H. Either it's missing a vertex or missing an edge, or both. In our second definition here, let G, which is V and E, be a graph, and let W be a subset of V. The subgraph induced by W is H, which has W and F, where F contains each edge in E that connects points in W. So both endpoints of edges in F have to be between points in W. As an example, let's start with K5. Everybody's connected to everybody in K5. This is a connected graph like this, and we'll have A, B, C, D, and E. Let's suppose that we take these here, this would be a subgraph by taking A, B, C, and D, but not E. But it is not the subgraph induced by this collection, because to do that you would have to have this edge as well. So A, B, C, D, sure, this is the subgraph induced. By the set A, B, C, and D. It's possible to obtain subgraphs in certain ways. Suppose we have G as a graph, and E is an edge of that graph. We can form G minus E by taking the set of vertices here and the set of edges, but subtracting out that edge. You can do the same thing by subtracting a collection of edges, let's say E1. That's V with E, subtracting out all the edges in E1. You can also throw edges in. You can add to this the edge that contains this new edge here. We can also make edge contractions. Suppose we're given the graph 1, 2, 3, 4, like this, A, B, C, D. If we contract the point C over here to the point B, contract this edge, then what's left over? These all get contracted down. This contracts down to the edge AB, and you can see all that's left are these edges here. We could have contracted A over to C. That would have left us this triangle. You have to be only a little more careful when you're removing vertices from a graph, because you have to subtract off all edges that connect to the vertex that you're going to eliminate. So you can have V minus some particular vertex, but you're going to have E hat, where E hat has all edges connecting to V removed from the set of edges E. You can form the union by simply taking the union of the set of vertices and the union of the set of edges. Here we're assuming that these are simple graphs.